Hello dear students, welcome to the series of sessions where I am discussing few subtopics which are very important from the point of view of JEE Advanced. Few are important for JEE Mains also. In today's session, I have brought reduction methods of integration. I will tell you how you reduce the difficulty of a problem in one step or two step, and then using that same idea recursively, you finally solve that question for any value of n that is given in the question. Before I start my session, I will like to talk about Daksh, who got All India rank 15 in JEE Advanced 2025. He got full 120 marks out of 120 in Maths JEE Advanced 25, which is a rare feat achieved by any student across country. In fact, this doesn't happen every year also. He was student of Arambh 22-25, where I was teaching him for 3 years. The ideas behind this session actually came from the discussion I used to have with his batch. In fact, some of the ideas are of Daksh also. So motivation of this session is also to repeat that performance which was given by Daksh this year and you will be giving in the next year. Dear students, I am still occupied with my students of Arambh and Eklavya. Eklavya is a program where we train students for JEE Advanced only. Eklavya 2026 is for those students who will be writing JEE Advanced this year in 2026 May or maybe April, whenever exam happens. Okay, so this is the QR code I'm sharing with you, which is to join Telegram channel of Eklavya 2026. You will get all sort of information related to Eklavya. When will be the exam? When will be the entry test? And after entry test, when will be the result? And when will be the classes? So all sort of information you will find it here. So please join this channel. So dear students, let me start the session. So this is me, Surendra Sir. I am teaching maths for last 14 years. I have been teaching for JEE Mains, Advanced, Olympiads, CMI and ISI. So today's subtopic, as I was talking about, is reduction methods of integration. What are reduction methods of integration? It is actually one idea where we will be this is one idea which we will be applying in the questions of integration which are given in terms of small n or capital N, you can say, where n is natural number, a bigger natural number, you can say. You may not be able to solve that integral directly, but you can reduce your integral, let's say in in terms of n, in terms of in minus 1 by reducing by 1 power, or that n can be in angle also. So you will be able to reduce that integral in terms of n from n to n minus 1 or n minus 2, and that same idea you will be repeating recursively to get your in finally in terms of I1 or I0. For n is equal to 0, if you know that value for I1 or I0, I think we are done. We can find now in finally in terms of the known values. So this is the idea. In this process, mostly we will be using integration by parts. So I have taken few instances which I feel you must know, starting with some algebraic formats and then trigonometric formats. So this is one idea where we are given in is equal to 0 to 1 minus x power 4 whole power n dx. Now if you want to do this integration, maybe one idea could be that for any given n we can open it by binomial theorem, then term by term integration. We will be able to get integral of each and every term, and you add them, you will get the answer. But that cannot be very simple, because if n is, let's say, 10, then there will be 11 terms. In fact, if it is 10, then 10C0, 10C1, all these terms will come and the values are very huge. So it is not that simple. So how we can do it with the help of reduction methods, please see. So I will be writing this in as, first of all, this n coming from the power over this bracket. Okay, so I am writing it as 0 to 1, 1 into 1 minus x raised to the power 4 whole raised to the power n dx. Now 1, let me take this as a second function, this as a first function. So by parts. So 1 will be having integral x This is 1 minus x raised to the power 4n, 0 to 1, then minus 0 to 1, integral of 1 is x, differentiation of this n into 1 minus x raised to the power 4 whole power n minus 1 into minus 4x cube dx. Okay, now if you put 1 and 0 here, I think we get 0, 0. So this will be just 0. Here minus, and this minus becomes plus, and 4n I can bring out. And then 0 to 1, it will be 1 minus x raised to the power 4n minus 1. And this x power 4, which I can write it as 1 minus x power 4 dx. Okay, so here you can see this in is becoming 4n outside. Yeah, so this is 4n outside, and if you multiply this bracket with 1, so I think first thing can be written as in minus 1 and then minus in. Okay, now if you take in on the other side, I think we will be getting 4n plus 1 into in, and that is equal to in minus 1, and I think into 4n also there. So finally, the expression for in would be 4n upon 4n plus 1 into in minus 1. Now, if you want to write it further, there is no need to do this calculation again. Just by looking at this expression, I can say if in was 4n upon 4n plus 1 into in minus 1, then this in minus 1 would be 4 into n minus 4 upon 4n minus 3. Okay, into in minus 2. So this way you keep on writing it, and finally your answer will be in terms of I1 or I0, you can say. In fact, this I1 and I0 values are very easy to find. I1 is just 0 to 1, 1 minus x raised to the power 4 dx. So the integral of 1 will be 1, integral for x power 4 will be, I think, 1 upon 5. So this becomes 4 upon 5. We could have found I0 also directly. I think in this case, it will be just integration of 1. So putting the values will give you 1. So it is up to you whether you want to write in terms of I1 or I0, but eventually you will be able to get this in completely for any value of n. Okay, now I will tell you the alternate method also, and then I will like to link the two results. That can be one good I will say learning for you, that how we can create some identities with the help of integration. Okay, now if you do this question with the help of, let's say, binomial expansion, and let me do it for not for all n, let me take this for I5, small value of n I will take. So if I take it for I5, it will be 0 to 1, 1 minus x raised to the power 4 raised to the power 5 dx. Then I can write it as 0 to 1, 5c0 minus 5c0x, 5c1x plus 5c2x square, and so on. In the last, I think it will be minus 5c5x raised to the power 5 dx. Okay, I think I have done something wrong here. Yeah, I have done many wrong things here. So the powers will not be x, it will be x power 4 here, it will be 8 here, and it will be 20 here. Now, if you do the integration, this will be 5c0 into x, 0 to 1 limit, so it will be just 1 only. Here 5c1 into 1 upon 5, then 5c2 upon 9, and so on. In the last, it will be 5c5 upon 21. So this is what we are getting if we do it by method of binomial theorem. But as I was telling you, this I can write, suppose this is I5. So as we have seen in our previous slide, this in is 4n upon 4n plus 1 into in minus 1. So 4n means it will be 20 here, 4n plus 1 means it will be 21 here, into I4. Now if I have to find I4, I think I can do it again. It will be 4n, so it will be 16 here upon 17. Once again we can apply for I3, it will be 12, this will be 13. Then for I2 we can apply, it will be 8 upon 9, Okay, then for this will be, this was after this is 4, this was 3, this was 2, this is 1, or maybe I can write it for 0 also. So it will be 4 upon 5 into I0. Yeah, correct. Okay, and I0 is 1. So you can see this expression which we have got in terms of binomial coefficients should be equal to this 4. I can take common 5 times, I think. 4 I can take common 5 times, and after that it will be just 5 factorial, I suppose. And in the denominator it is 21 into 17 into 13 into 9 into 5. So this binomial expression, this expression in terms of binomial coefficient has to be equal to this thing, 4 power 5 into 5 factorial upon this thing. Okay, so I have discussed one more thing after doing that reduction method, that how you can connect this result with your binomial coefficient expression. This binomial coefficient expression is not easy to find otherwise. You can imagine there are 6 terms and they all are having 21 all sort of numbers in the denominator, so solving it will not be that easy. In fact, if this was not 5, it was, let's say, 10 or 20, then it will even become more difficult. So this will get you the expression for this kind of binomial expression. Okay, now coming to one more example on this algebraic format only. Here we are given in is equal to 0 to 1 dx upon 1 plus x square whole power n. Now, if n is 1, then I think it is very simple, tan inverse x. But if n is 2, even for n is equal to 2, it is not that direct to do. You have to do some trigonometric substitution, then you can do it. For higher value of n, it will be difficult to do even with the help of trigonometric substitution also. Because when you do trigonometric substitution, the expression in terms of n will be something that is to be done with the help of reduction method only, which I will be discussing in trigonometric formats just after it. But let's see how we can do it. In this method also, it will be done with the help of integration by parts. I can take one as second function, and this 1 upon 1 plus x square whole power n as a first function. This is first function, this is second function dx. Okay, and then this one will be having integration as x. This we will be writing as it is, minus 0 to 1, integration of 1 is x, differentiation of this would be minus n upon 1 plus x square whole raised to the power n plus 1, and then 2x also will come from the differentiation of 1 plus x square using chain rule. So here we will be putting the value 0 to 1. So if you put the value from 0 to 1, we will be getting, for 1 it will be 1 upon 2 raised to the power n, for 0 it will be 0. Okay, and then this can be written as minus minus plus 0 to 1. I will write 2n common, and then x square we will be writing as x square plus 1 minus 1 upon 1 plus x square whole raised to the power n plus 1 dx. Okay, now let me solve this question here. Let me use this space. So this in is coming out to be 2 power minus n, okay, plus 2n if I take common outside. So x square plus 1, if I write it separately, divided by 1 plus x square power n plus 1, I think this will give you in only, minus it will be in plus 1. Okay, now you can say, rather than reducing it, we have actually increased the difficulty level by saying in terms of in plus 1, but you can write it in reverse order also. You can say 2n into in plus 1 here, okay, will be equal to 2 power minus n plus 2n minus 1 into in. So this is my reduction method for in plus 1 in terms of in. So you can write in also in terms of in minus 1. So in this, I think option A seems correct. 2n into in plus 1 is equal to 2 power minus n plus 2n minus 1 in. Okay, and also they're asking I2 and I3 values. So let's find them. So for I2, I think if I take n is equal to 1 here, n is equal to 1 here. So this will be 2 I2. and for n is equal to 1 this will be 2 power minus 1. For n is equal to 1 this will be just 1. Okay, and I1 I will write separately. I1 is just tan inverse x, tan inverse x starting with 0 going till 1, so it will be pi by 4. Okay, so this is 1 into pi by 4. So what will be I2 here? I2 will be 1 upon 4 plus pi upon 8. 1 upon 4 plus pi upon 8. So B also correct. Now if we have to find I3, so here we will be putting n is equal to 2. So n is equal to 2 will give you 2 into 2, 4. I3 is equal to, if you put n is equal to 2, it is 1 upon 4. If you put n is equal to 2, this will be 3 here. And if you put n is equal to 2, this will be 1 upon 4 plus pi by 8. So this will be, you can write 1 by 4 plus 3 by 4 as 1 plus 3 pi by 8. And this is the value for 4 times I3. If you are looking for I3, it will be 3 pi by, I think that option doesn't seems to be correct. Okay, maybe I think everything fine. So only A and B are correct. You can check the calculation also. Now coming to trigonometric formats. Now I'll be starting with this 10 power nx. Very easy to understand. Maybe many of you must be knowing it already. Now if you want to do this in is equal to 10 power nx dx, this will not be done by integration by parts. Rather, it will be done using 10 raised to the power n minus 2x, and then remaining 10 square I will be writing it as secant square x minus 1, famous trigonometric identity. Then this 10 power n minus 2x into secant square, I think we can do this integration using substitution. Just I think you can write this as d of 10x also. Okay, minus the thing that is remaining, that is 10 power n minus 2x dx, can be written as in minus 2. So I have got in as the integral of this would be 10 of n minus 1x upon n minus 1 minus this is in minus 1. So not minus 1, this is in minus 2. So here we are reducing our problem by 2, not by 1, by 2. So I think it will become faster for us, in minus 2. Okay, so in is obtained that way in terms of in minus 2. You can add some arbitrary constant also, because it is always there in indefinite integration. Here, if you want to know what will be my I1, because depending upon n is even or odd, you will be landing up at I1 or I0 in the end. I1 will be integral of 10x, you know it is log secant x dx, so log secant x plus c, and if it is I0, it is just integral of 1, that is x plus c. Okay, so this is how you can do it. In fact, I2 is also easy to find. It is just 10 square x. So 10 square will be written as secant square minus 1. So that will be 10x minus x. So that can also be used if you want to use I2 directly. Okay, so I hope you have understood the idea. Now there is one more thing to this question only, that if you are given this integral with limit 0 to pi by 4. If I make this question of definite integration where limits are given like this, and suppose this is in is equal to 10 nx dx. In this case, this relation of in will be equal to, because we will be putting pi by 4 here, so it will become 1 upon n minus 1 minus in minus 2. So in this case, the result is in plus in minus 2 is equal to 1 upon n minus 1. Okay, so very important thing, please, you may like to remember it. I will not say exactly remember it, but I will say you should have something related to this in your mind whenever you are looking at this question. It should not be that you are doing it for the first time in the exam. Then it may become a bit difficult, because this can lead to many other questions also. So it should be there in your memory. Now cot power nx or cot power nx from pi by 4 to pi by 2, they are exactly same as 10. You just have to write cot power n minus 2 into cot square will be cosecant square minus 1. So it is same, I am not doing it. Now secant power nx. Now how this will be done? I think this is also done Similar way, we will be writing secant power n minus 2x into secant square x. Just 1 minute. Just 1 minute. Secant square x. Yeah. I will be writing that way only. But after that there is a change. You will not be doing by the method we did in for 10. Rather, we will be taking this as a second function and that as a first function. So integration by parts. So my second function integral would be 10x. First function will be written as it is, minus integral. Integration of 10 secant square is 10x, and differentiation of this would be n minus 2 into secant of n minus 3x into secant x 10x using chain rule dx. So this is the thing that we are getting after minus sign inside integral sign, integration of second function, differentiation of first function. Okay, now this is 10x into secant raised to the power n minus 2x minus n minus 2. If I take common, it will become 10 into 10 square, which I can write it as secant square minus 1. So this will become secant power nx. See, this 10 into 10 is 10 square, which I am writing it as secant square minus 1. And if we multiply that secant square minus 1 with this thing, it will be 10 secant power n minus secant power n minus, I think, 2x dx. So we are, I think, done. We have got in as 10n 10x secant power n minus 2x minus n minus 2, and this you can write it as in minus 2. So combining in term here will give you in terms of in minus 2. I'm leaving at this step. You can simplify it. In fact, I have given the final result in my session notes also. Okay, now similar to secant, I think we have cosecant power nx also. That is also very similar. So I will not be doing it. Then comes sine power nx. That's very important, because after doing this, I will be coming to one result of definite integration. One Wallis formula will also come. Then I will talk about beta function and gamma functions also. So let's see how in is calculated using reduction method. In this case, we will be writing sine x into sine power n minus 1 x dx. Okay, this I will take as a second function whose integration is to be done, and this I will be taking as a first function. So this becomes minus cos x integration, and this will be as it is, sine power n minus 1x minus integration for sine, the integration is minus cos x. For this, the differentiation will be n minus 1 sine raised to the power n minus 2x into cos x dx. Okay, so this becomes minus cos x sine raised to the power n minus 1x minus plus, you can take n minus 1 common, and this cos square we will be writing it as 1 minus sine square x dx. So this in here will become minus cos x sine power n minus 1x plus n minus 1 into, I think this is in minus 2 minus in only. Yeah, in only. Okay, now if I take this in on the other side, let me do it completely. I will write here on the top. Okay, so if I take in on that side, I will be getting n times in, and that will be equal to n minus 1 into in minus 1 minus cos x sine raised to the power n minus 1x. And you can take some c also. Let me remove this n from here. We will be getting this whole divided by n also. So this is the relation for in terms of in minus 1. Okay, now one very important result that comes after this. Cos power nx is also very similar. There is no change, just write cos in terms of in place of sine, that's it. And so the important result that I was talking about was when this is 0 to pi by 2. When this is 0 to pi by 2. So as I was talking that in is this thing n minus 1 into in minus 1 upon n. If limit is from 0 to pi by 2, the limit 0 will make sin x 0, the limit pi by 2 will make cos 0. So this will go. So my in will be just equal to n minus 1 upon n into in minus 2. I think it was 2. Yeah, difference of 2. Oh, I have made a mistake here. It will be 2 here. Okay, so in is coming out to be like this. Now if you want to repeat it, okay, that will be n minus 1 upon n into n minus 3 upon n minus 2 in minus 3, and so on and so on. We can keep doing like this. So finally my in will be n minus 1 upon n into n minus 3 upon n minus 2, and so on, depending upon n is even or odd. If n is, let's say, even, in this case, in this numerator, it will be 3, it will be 4 in your second last term, and then it will be 1 upon 2. Okay, and then it has to be I naught. If n is even, it has to be, okay, I have made a mistake here also. I think today something is going in my mind. This would be in minus 4 because we are reducing it by 2 every time. So here it will be I naught. Okay, and dear all, I naught, I think it is very easy to find. Your integral will be just integration of 1, so it will be pi by 2. So this you can write it as pi by 2. If your n is odd, then it will be like this, and so on. Here you will be having 4 upon 5 and then 2 upon 3. And then it will be, I think, I1. It will end at I1 here. Okay, and what is I1? I1 is just integral of sin x from 0 to pi by 2, which is equal to 1. So this is how this can be written directly. And that is one very important result I will ask you to remember. Dear all, in this in, I tell you one idea. You may follow it. It is a reverse numbers written here. You can see n minus 1, n minus 2, n minus 3, n minus 4, and so on till you reach either 1 or 2. If you reach 1, then here there will be I naught, which is equal to pi by 2. Or if it is 2, then it will be I1, which is nothing but 1. So you can now see, if you go that way, it is 1, 2, 3, 4, 5, 6, 7. But numerator, denominator, numerator, denominator, that way you can say 1, 2, 3, 4 or 2, 3, 4, 5, 6, 7. Starting with always n here in the beginning, then reducing by 1 here, then reducing by 1 once again, then reducing by 1, and so on and so on. You will get this in, and it is very important you to remember. In fact, these two are equal. They are equal if it is 0 to pi by 2, because by King's rule, sine becomes cos if limit is from 0 to pi by 2. Okay, now im comma n, where there are two unknowns or two powers, one is on sine, one is on cos. Now how to deal with this? Now you can obviously not do it in one go. Yeah, there is a possibility. Suppose n is odd. If n is odd, then what you can do, you can write your cos x into cos power n minus 1, which will be even power of cos. You can convert cos square as 1 minus sine square, and then everything will be in terms of sine. So you can do this integration by substitution. If n is odd, then by substitution is possible. I think sin x equal to t you can do. If m is odd, same explanation, but you have to put cos x as t, and you can do by substitution also this thing directly, but both are even. In fact, the method which I am going to tell you will cater both cases, even, odd, even, whatever. But if one of them is odd, then I will say more practical, more easier way will be by substitution and not by integration, by reduction methods. Okay, so let's see how it is done. In this case, what we will be doing, we will be writing 1 cos along with this sine, and then remaining power of cos here. Now you can see if I take this as a second function, we can do the integration easily, because taking sin x as t, cos x dx will become dt. So this integration is very easy. In fact, I can write it directly, sine power m plus 1 x upon m plus 1, okay, into cos n minus 1 x, first function as it is, minus the integration of this thing, that is sine m plus 1 x upon m plus 1, and this, its differentiation would be n minus 1 into cos raised to the power n minus 2x into minus sin x dx. Okay, so this I m comma n has become sine raised to the power m plus 1x upon m plus 1 into cos of n, cos power n minus 1x, minus, I can make minus minus plus, and this n minus 1 upon m plus 1. And here you can see this sine x, if multiplied with here, you will be getting, let me write it directly, let me not write it as an integral, rather let me write it as I m plus 2 comma n minus 2. Okay, so what we have done by these two steps, we have reduced, or rather I will say changed this I m n in terms of I m plus 2 comma n minus 2. So you can say you have reduced the power of cos, definitely, but you have increased same power of sine. So how this can be reduction? Actually, theoretically, not practically, I will say, theoretically what we are going to do, if this kind of question is to be done using reduction methods of integration, first you will reduce all the power of cos. It will go till 0, because we are doing it mostly when n is even, so cos term will go, then all the powers will be there on sine, and then we will be using the method I discussed it here. When all the power is on n, the power on sine will be m plus n. So then you will be using the earlier one. You can say this seems very large, but if there is no option, and before we conclude that this integration cannot be done, we may have to this also. We may have to do this also. In fact, although this is not a very doable thing for indefinite integration, but this is very much doable for definite integral if your limits are from 0 to pi by 2, and that is called Wallis formula. That is called Wallis formula. So suppose you are going to solve for 0 to pi by 2 sine mx cos nx dx. Okay, and this is I m comma n. Okay, now if I put 0 to pi by 2, you can see this will again be 0. So here we will be having n minus 1 m plus 1, n minus 1 in the numerator, m plus 1 in the denominator, I m plus 2 n minus 2. Okay, once again if I do the same thing, this will become n minus 1 and then n minus 3, whereas in the denominator it will be m plus 1 and m plus 3. Okay, and then it will become I m plus 4 n minus 4, and so on till this becomes 0 or maybe 1. So you can see after reducing it, after reducing only in terms of sine power, you can then finally you can find the result of this finally. Although this is a small, this is not a very small method, I will say, but after doing with this method, we get one result, which is one very important result known as Wallis formula, and we must know this. What is this? Please see. I m comma n comes out to be, please see, in numerator you will be having one expression for n minus 1. So starting with n minus 1, then n minus 3, and so on. This will end at either 2 or it will end at 1, depending upon your n is even or n is odd. For even it will end at 1, if it is odd it will end at 2. Similar bracket will be there for m also. So here we will be having m minus 1, m minus 3, and so on. This will also end at either 2 or 1, depending upon m is odd or even. Now in denominator, it should be starting with m plus n. See here, once all the powers has gone to sine, or in the end one power is there on cos, you can do it directly. And when you solve till the last step, you will see the final result will come like this: m plus n here, m plus n minus 2 here, and so on. It will be in the end either 2 or 1. It again depends on whether m plus n is odd, even or odd, okay, into some k number. I am writing it here, and that is how this Wallis formula is written always. This value of k, this value of k is pi by 2 or 1. It is pi by 2 if m and n both are even. If they both are even. You have seen why pi by 2 was coming in previous case also, where I was deriving sine nx dx. We got I naught as pi by 2. So this is a case when n becomes even. With the same reason, because of the same reason, you will see when both m and n are even, this k will become pi by 2 and it will become 1 if otherwise. Otherwise means any other case out of 4. M even, n odd, m odd, n even, or both odd. In this case, it will be 1, otherwise it will be pi by 2. Now this can be very useful thing, because many question I have seen, when you do some substitution, your integral converts into this form 0 to pi by 2, and you can directly find the result using this I m comma n, which we call as Wallis formula. In fact, I will talk about beta function also. That is also very much similar to this thing. Let's see what is beta function, how it is different from it. I will also talk about the importance of knowing gamma function and beta functions. Okay. Now, next trigonometric format is sine nx upon sine x into dx. This is one very, I will say, tricky thing. When I did this for the first time, I was stuck. Honestly speaking, I could not think of how it will be done. So I took some time. Then how it was done, please see. You can write in minus 2, the difference of 2 here. Okay. In this case, it will become sine nx minus sine n minus 2x n minus 2x, and in the denominator sine x, because denominator is same, it is independent of n. In this case, sine c minus sine d formula we can apply. So this becomes 2 cos c plus d by 2, which becomes n minus 1 x, and then sine c minus d by 2, so sine x upon sine x dx. Now sine x can be cancelled, so you will be getting the integral to be 2 sine n minus 1x upon n minus 1. Okay, so what we have got in is equal to this plus in minus 2. Now we can repeat this thing. For in minus 4, in minus 6. So ultimately we can find in terms of maybe only sine terms or n terms, you can say. So this is how this is done. In fact, there is one very important part of this integral when it becomes definite integration from 0 to pi. If it becomes from 0 to pi, then also it is very important. You can see if it is from 0 to pi, then this in, you can see, will be equal to in minus 2, because this will be 0. N minus 1 will be integer, so sine pi, n pi or whatever pi, it will be 0, and sine 0 is also 0. So all in minus 2, in minus 4, they are equal. Now this in will end either at I naught or it will at I1, depending upon n is even, then I naught, and I naught you can see will be just 0, because I naught means 0 dx, so 0. I1, if you take n as 1, it will be sin x upon sin x, so 1, so it will be pi. So this is when n is even, and this is when n is odd. Okay, so in this case, all in minus 1, in in minus 2, in minus 4, they all will be equal. I naught, I1 you can directly say. So you can conclude what will be the value for general in. You can talk about I100 also will be 0. I99 will be pi. I1001 will also be pi. So that way I think we can write the answer for this. Now, one more this reduction method format in trigonometry I have taken, where we are having sine square nx upon sine square x dx. I have taken this as jx here. There is a reason why I have taken this as jx. Please see, I can write jn actually jn minus 1. I can write this as sine square nx minus sine square n minus 1x upon sine square x. If you use the result sine square a minus sine square b, which is sine a plus b, which will be 2n minus 1x into sine a minus b, so just sine x, upon sine square x dx. So 1 power of sine x will cancel, and we will be getting this as sine 2n minus 1x upon sine x. Now you can compare it with my previous format in of this point number 7. This is actually I2n minus 1 actually. I2n minus 1 of 7 number. Okay, now we know how I2n minus 1 is solved. So you can find Jn in terms of I2n minus 1, and then Jn can be found. Okay, in fact, if this becomes, if we are given Jn from 0 to pi, okay, if we are given this from 0 to pi, so sine square nx upon sine square x dx. In this case, you can very easily see Jn minus 1. Here the gap is of 1 only, not 2. It will be I2n minus 1. And for I2n minus 1 means it will be odd number, and we have seen for odd value it is equal to pi. Okay, so this will be equal to pi. So you can see difference of two consecutive Jn and Jn minus 1 is of pi, which means your J1, J2, J3 and so on should be AP. Should be AP whose common difference is equal to pi. And also we can find J1 directly. J1 we can find directly. It will be, I think, pi only. Your sine square x upon sine square x, 1, 0 to pi, J1 will be pi. So if first term is also known pi, common difference is pi, I think we can say Jn, the general term, will be n pi. So for this integral, if it is done from 0 to pi, Jn will be n pi, that's it. So that is also important. I have seen this kind of question asked in many tests. Although JEE, they have not asked directly, but in many tests of different coachings, I have seen they are asking this kind of question. And it's a good understanding. Actually, it's a very good concept to remember because it can come maybe some otherwise. Okay. Now, as I was talking about gamma function. So let's see what gamma function is. First of all, you take this as a question. Okay. Because when I teach in my class, I normally do not recommend gamma and beta functions very strongly. You can manage without them also, but if you can remember it, okay, you will see the beta function will be connected with gamma, and beta will be related to Wallis formula. So Wallis formula, gamma function, beta function, they will be related, and there are few values. If you remember them, I think the use of gamma function, beta function will make questions easy for you. Okay, please see how. First of all, this gamma n coming from power of x, but please see, gamma n is not directly taking the power of x. If power is n minus 1, then we are taking n here. So the power is here 1 less than the number n, we are taking it here. Okay, now this we will be doing once again by parts. How? We will take this as a first function whose differentiation will be done, and this I will take whose integration will be done. Okay, so its integration is e power minus x with minus sign into x raised to the power n minus 1, and limit from 0 to infinity. Then minus 0 to infinity integration e power minus x with minus multiplication into n minus 1 into x raised to the power n minus 2 dx. Okay, now if you put infinity, e power minus infinity will tend to 0, x power n minus 1 will tend to infinity, but still exponential function being very powerful, you can say this limit will tend to 0. You can do it with the help of LH also. You can write e power minus x into x raised to the power n minus 1 as x power n minus 1 upon e power x. And now you can see at x tending to infinity, this is the form of infinity upon infinity. If you differentiate once, e power x will not change, but 1 degree of x power n minus 1 will change, reduce actually. Once again, if you use LH, so every time you reduce your term here will reduce in degrees, this will remain same. So ultimately this will become some constant divided by e power x, x tending to infinity, this will be tending to 0 as x tend to infinite. Okay, so this will be 0 only, whereas this is minus minus plus, I can take n minus 1 outside, and if you notice 0 to infinity e power minus x, x raised to the power n minus 2 dx. Now if you notice this expression, this integral with this integral, I think we have got something here. This is n minus 1, this is gamma n minus 1. The power has reduced by 1, everything else is same. So gamma n is equal to n minus 1 into gamma n minus 1. So this means if this kind of integral is given, okay, we can further write gamma n as n minus 1, then n minus 2. This will be gamma n minus 2. In fact, I can keep writing n minus 1, n minus 2, and so on. I think it will go till 1, assuming n is natural number. I think it is natural number, although this gamma function is defined for otherwise also, but for our purpose, let's stick to n belongs to natural, and I will give you result for n is equal to half also. Okay, so in that case, it will be gamma 1 here. Okay, so this becomes n minus 1 factorial into gamma 1. Okay, now gamma 1 value can be found directly also, as I was talking about. It will be just 0 to infinity e power minus x dx. Integral minus e power minus x, limit from 0 to infinity. If you put infinity, you get 0. If you put 0, you get minus 1. And sign of minus because of lower limit, so it finally becomes 1. So here you can see this is becoming n minus 1 factorial. So gamma n is n minus 1 factorial. Just remember. But you have to remember this expression also. Otherwise, there is no point. Okay, you have to remember this expression, this integral also, that what is gamma n. Okay, and gamma n is n minus 1 factorial. Okay, so this we will be using in beta function also. So you may remember it. Please see. Now, coming to beta function. So let me write gamma n here was n minus 1 factorial. Okay, and one more thing I would like to write it here. If n is natural number, okay, and gamma half value is also under root pi. You can remember this directly without proof, because in some questions you may have to use gamma half value also. So gamma half is equal to under root of pi. Actually, it is coming from that integral 0 to infinity e power minus x square dx, and this is also having some different method which I will not discuss in today's session, maybe some other session. This comes out to be, if I'm not wrong, root pi upon 2. Okay, so using that you can get this also. Okay, now beta function. Now what is beta function? Beta function is 0 to 1 x power m minus 1 into 1 minus x power n minus 1 dx. Looking quite simple thing, x 1 minus x. Okay, now if you use King's rule, where we replace x by a plus b minus x. Okay, so here x will be replaced by 1 minus x. So you can very easily see this will be equal to beta n comma m also, because this will become 1 minus x, this will become x. So beta m comma n will be beta n comma m. Now it doesn't matter whether m is there on x or m is there on 1 minus x. One of them should be m, one of them should be n. Then we call this as beta m comma n. Okay, now there is a result of beta m comma n with gamma function, and this is actually equal to gamma n gamma m upon gamma m plus n. Okay, I will give you a very simple proof of it, but please remember beta function n comma n or n comma m, it's same thing, is equal to given by this thing. Okay, it may give you a feeling of NCR, reciprocal of NCR, m plus n and m. Okay, so beta n comma n given by this thing. Now if somebody is asking you for some integral value like 10 or 15, I think with the help of this result, I think this integral is now found directly. Okay, see, there can be debate, should we remember it or not? So I will say it is not very much used, but it can be used sometimes. So it will be better you keep this in your memory. Then you will save your time, your answer will be very quick. Okay, but if you do not remember it, you have to derive it. The use of this in JEE Advanced has not been very huge, I will say, but I will say it is worth remembering this result because it is connected to many things. Okay, now how this thing is coming, please see. To derive beta mn, what we will do, we will write x is equal to sine square theta. Then dx becomes equal to 2 sine theta cos theta. Okay, so beta m comma n, you can see, will be limit 0 to pi by 2, because when x is 0, theta is 0, x is equal to 1, theta is pi by 2. Now x is sine square theta, so it will become sine raised to the power 2m minus 2, and 1 sine theta will come from dx also, so 2m minus 1 theta. Similarly for cos, 2n minus 1 theta d theta, and this 2 will also come, we can write it here. Okay, now you can see this is exactly similar to what we did in Wallis formula. Okay, so what was Wallis formula? Let's try to recap that. I think here it will start with 2m minus 1 minus 1, so 2m minus 2. Then you will reduce it by 2 all the time, so 2m minus 4 and so on. And this is even number always, so it will end at 4 and then 2. Similarly for 2n minus 1, it will be 2n minus 2 first, then 2n minus 4, yeah, 2n minus 4 and so on. This will also end at either at 4 into 2. In the denominator, it will be sum of these two. So 2m plus 2n minus 2, and then you reduce it by 2. So 2m plus 2n minus 4 and so on. This will also end at 4 into 2. Okay, now if I take 2 common from all of them, I think 2 will be common, m minus 1 times here. So 2 raised to the power m minus 1. 2 will be common, 2 raised to the n minus 1 times, so 2 power n minus 1 here. Whereas in the denominator, it will be 2 common, m plus n minus 1 times. It will be 2 raised to the power m plus n minus 1. And after that, I think I can write it directly because it is m minus 1 factorial after that. So it is gamma m. And this is n minus 1 factorial. So this is gamma m. And for this, it is gamma m plus n. And you can see these powers are getting cancelled. So we are getting this beta mn is equal to this thing. Okay. Normally people do this kind of integration. If they are given in the exam, they put this x is equal to sine square theta. I also recommend my students that if you cannot remember beta function, first of all, I will say it will be better that you remember it, but in case you forget or whatever, you put it as sine square theta and then go into that Wallis formula. But not remembering Wallis formula is not option at all. You have to remember it. That is very, 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 very important. Please, 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 please remember it. Okay. Now I have taken 2 PYQ questions. Although I didn't find questions in recent years, but I think they have been asked. In fact, the idea is very important. Can be used in questions of areas also, or somewhere else also, or You cannot say whether they cannot ask this kind of question once again in this year. So this is a question of 2003 PYQ JEE Advanced 2003. JEE Mains, they have asked many questions that I have not included. So this is a question which they are saying I m comma n t power m and 1 plus t power n dt. It looks like a beta function, but it is not actually, because if it was minus here then it will be beta function. This time it is not. Now we have to find I m plus n comma n minus 1. I think something similar to this we have done in this session itself. So how we will be doing it? We have to increase I m plus 1, we have to increase m to m plus 1, and I have to decrease the power n. So I will be taking this as a second function, I will be taking this as a first function. So I m comma n will be equal to 0 to, sorry, not 0 to, first function as it is 1 plus t raised to the power n. Second function integration is t raised to the power m plus 1 upon m plus 1, and here we will be putting 0 to 1 minus integral 0 to 1 and 1 plus t raised to the power n minus 1 into n differentiation, and this t raised to the power m plus 1 upon m plus 1 into dx. Now if you put 1 here, you will get 2 raised to the power n upon m plus 1 minus 0, no need to write that, minus this will be n upon m plus 1, and then I think it is nothing but I m plus 1 comma n plus 1. So is there any relation like this? Actually you have to write I m plus 1 comma n minus 1 in terms of other thing. Okay, so oh sorry, they're asking I m comma n in terms of this only. Okay, I think we are done. So 2 power n upon m plus 1 minus n upon m plus 1 I m plus 1 comma n minus 1. It just looks like 1 is correct. B is different, this term is not there. In C, instead of minus there is a plus sign. I think this minus is correct. Yeah, correct. D is also wrong. So answer is A. Okay, one more question I will take. That is a question of 2006. Very important question, I will say. In this question, what they have asked, they are asking the ratio of these two things, in which both integral are having 1 minus x power 50, but in one of them its power is 100, in one of them power is 101. So it looks like we just have to reduce the power from 101 to 100, and we have to take the ratio. Okay, so what we can do, we can start with this I 101 maybe, and this will be 0 to 1, 1 into 1 minus x raised to the power 50, 101 dx. So second function, first function, so x into 1 minus x raised to the power 50, 101, 0 to 1 minus, and then 0 to 1, integration of 1 is x, differentiation of this is 101, and 1 minus x raised to the power 50 power 100, and then minus 50 into x power 49. Okay, so this is what we are getting here. Let me see if all is correct or not. X 101 power 100 minus 50 x power 49 dx. Yeah, that's correct. Here everything becomes 0, upper limit, lower limit both become 0, minus minus plus, so we get 50 50 here, I think 50 50, 101 into 50 minus minus plus. So what is here now? 0 to 1, x into x power 49. Okay, so this will be, I think I can write it as 1 minus x power 50 into 1 minus x raised to the power 50 dx. This is 100 actually, 100 only. So this will be 50 50, and if you multiply this one with this, you get I 100. If you multiply this with this, you get I 101. I think it is same thing that I took as my first example in this session. Okay, so if you take 101 that side, we will be getting 5051 I 101 equal to 5050 into I 100. So this is what we are getting. Now what they are asking? They are asking this upon this only. Actually they are asking 5050 I 100 upon I 101. So this becomes, I think, 5051. I think that's the answer. Okay. There can be more ideas related to reduction method, which I have not taken in this session. So not to increase the length of this session maybe, but I will share 2 or 3 more ideas in my session notes. Please go through it. Okay, so that is all for today regarding this reduction method. I will come again with new topics, new subtopic in my next session. Till then, bye bye. Take care. Thank you so much.